Welcome everyone to the talk today. My name is Pramod Immaneni. I'm a senior architect at DataTorrent and a PMC member of Apache Apex open source project. So with that, I'd like to talk about Apache Apex. So I would like to start talking about Apex by briefly going into the history of Apex. So what is Apex today was originally developed at DataTorrent. The founders of DataTorrent are ex-Yahoo Finance, and they had experienced firsthand the problems with large amounts of data, especially when it is coming at you really fast and has an expiry time to it. So it's of no use if you don't process it quickly enough. This was also the time when Hadoop was coming up and becoming popular, and Yahoo were one of the pioneers. So the founders, they decided to actually build a platform that would run natively on Hadoop and be able to enable a diverse set of applications that can fully deliver on the promise of Hadoop, both compute and storage, and at the same time be highly operable. So the first versions of the software were actually ready when Hadoop 2.0 Yarn was still in the alpha stage. And when we released our software, when Yarn became GA, we were the first application other than MapReduce, which of course came with Hadoop 2.0. So, so we are basically very early in this, in the space. And then last year we open sourced the platform to Apache, and I'm actually happy to say that a couple of weeks back we graduated to become a top level project. So now we are a top level Apache project. And over the last 8 months, since we started the project till graduation, we've actually seen the interest and participation grow in this open source journey, whether it is meetups or new contributors joining the project. And we have continued our commitment to the project, and we are still deeply involved. So today's talk, there are going to be two parts. First, I'll do an intro into Apex. Then in the second part, I'm going to do a more hands-on application building on top of Apex. So with that, let's go into what Apex is and dive into it. So what's Apex? So Apex is a platform and runtime engine that enables development of scalable and fault-tolerant distributed applications. So the platform comes with an API that lets you build diverse set of applications. It's Hadoop native, so all you need is Hadoop. No other pieces of software are needed. It runs, it uses all the facilities that Hadoop provides, and doesn't require any other external components. It can be used for processing streaming, real-time streaming data in motion, or it can also be used to process batch data like files. And its strength is in when it's processing high throughput data. Think about millions of events per second or even higher, and it can equally well process lower throughput data, not a problem, and still deliver low latency, end-to-end low latency. And it also comes with a rich library of commonly needed business logic, so you don't have to always write things from scratch. And it gives you the full freedom to write any custom logic in your application. And it could basically write any Java code. So we have a question. When you say Hadoop native, apart from HDFS and Yarn, what other components are required? So when I say Hadoop native, you're right. Those are the only two components, HDFS and Yarn. Nothing else is required. Okay. Good question. So I'll go to the next slide. So what do applications written on top of Apex look like? First of all, they would be distributed. So your logic, your application logic, you break your application logic into smaller components called operators, and these operators are then run across the different nodes in your cluster. Um, so they're running distributedly, and Apex is handling all the data transfer between them, and all the fault tolerance and scalability, which I'll come to next. So it's scalable. So each of your operator can be broken into multiple partitions. So you can have multiple instances of your operator or multiple processes to handle larger amounts of data and to meet your SLA. The entire application is fault tolerant, would be fault tolerant. So any of your nodes go down in your cluster, or there's any other outage, it will not affect your application. We will be able to detect. So there's a runtime component of Apex that's running alongside your application. It detects which components have gone down or which operators have gone down because the nodes have gone down, and it will recover them to a to a valid state, and it will reset the processing only for uh, that affected portion and to an earlier checkpoint, which I'll go into detail later, and continue processing. So you don't have any data loss, nor do you have wrong calculations or duplicate data. And the most important thing is we preserve state. So if your operators have any long-term state, maybe they are computing some aggregates, they can keep that in memory, and you won't lose them even when there are failures, because we frequently persist your state and then recover it in case of failure. And you can have long-running applications. So we are actually saying that you don't have to shut down your application theoretically. So you just keep running them. So if, of course, if it's a batch application, you may want to shut it down, but if you're just doing real-time processing, you just continue running. And like I mentioned earlier, we provide a library of these operators that are out of the box. So if you need connectors to connect to the popular input-output sources, we have them. Um, if you want to do some computations, you want to do some algorithmic processing, we have many commonly needed operators. Or you can write your own using our API. And in fact, our operators also implement the same API. So there's nothing hidden. It's a well-defined API which lets you write your own logic. And on top of Apex, DataTorrent provides an enterprise edition of the software where it includes other tools such as our operational insight tool, which will give you a detailed real-time analysis of your application, where you can see every component of or every operator of your application, how it's performing, what it's doing, health, its statistics, and so on. And we'll look at that tool a little later. So this is a brief overview of how the Apex stack looks like. So as I mentioned, all we need is Hadoop. So you could be running on a physical cluster, a virtual cluster, or on cloud. You could be using any of the major Hadoop distros like Cloudera, Hortonworks, MapR. You could even be running Apache Hadoop directly. Does not matter. And I said we only need Yarn and HDFS that comes with Hadoop. And then on top of it, you have the Apex streaming runtime, and on top of it is your application. And on the top level, you'll see some of the value-added tools that DataTorrent provides in its enterprise offering, where we have the management console, that's the operational console. We have a graphical application assembly and a visualization dashboard if you want to have widgets that to visualize real-time data. And on the right side, you see REST API, which essentially is the backbone of our operational theme. We basically make sure that everything and every component is queryable, and you can actually know in real time what's going on, as opposed to it being a big black box, right? And you'll see some of it when I show you some of the tools. So here's an overview. Um, oh, so there's a question. Is Apex part of any distro? Um, we are working towards integrating it into BigTop, and I believe it's pretty close. Yeah, that's where you can find it. You can also download it as part of DataTorrent from our website, or you can go to the Apache Apex open source page. You can get the source from there, and you can also find some builds there. So this is a brief overview of our operator library. We have many operators, a lot of input-output connectors, you name it. Message queues like Kafka. In fact, Kafka is like a first class. We have a first class support for Kafka. We have a very deep operator that handles all the features of Kafka, like Kafka partitions, offset management, and so on. Uh, or if you're talking to JMS, any of JMS enabled queuing systems, ActiveMQ, you're talking to traditional databases, you're talking to NoSQL databases like Cassandra or MongoDB. So you'll find all those connectors. You'll find some social media connectors as well if you want to talk to Twitter. Lots of algorithmic operators as well, math, parsers, everything you see here. We also have some more higher level operators like deduper. If you want to dedupe a lot of across a lot of data, you want to do big joins, or if you want to do some large, if you want to have a large state in memory, and you want to have store a lot of data in memory as well. We have utilities for that. So uh, okay, so I have some more questions before I go to the next slide. Do we get Apex as a VM? Uh, you don't need a VM because you can just install Apex on any Hadoop distro. It's a simple installer. You install it on one node, and you can launch your applications from there. However, if you want to try something that's ready-made, packaged, on the DataTorrent website, we do provide a sandbox which is a VM with a single node Hadoop cluster with Apex and everything already installed. So that might be something if you want to give it a try to see how it looks. Um, there's a question in the previous slide. You have streaming engine on top of Hadoop. How does batch mode is handled? So the way I answer this question is batch a streaming engine, a good streaming engine can handle batch. Should be able to handle batch easily because streaming is just a faster way of processing events, and in batch mode you are essentially your events are just coming from a different source, which are in this many case it's files, and we do provide a lot of operators, high performance operators to read from files which are in the library. um, for example, we have operators that parallelly read from different blocks of the file, so you can get parallel processing. And we have actually even built applications, not just operators on top. We have an ingestion application that you'd find on our website that you can use to ingest data between, let's say, um, you can from, like, let's say, an NFS source into HDFS, or if you want to do HDFS to HDFS copy, you can do that. So you can find examples there as well. So let's see how how a running application on Hadoop, let's say run application built on top of Apex, how would it look on your cluster? So here's a sample topology of you have one resource manager from Hadoop, and you have four nodes, let's say, and worker nodes. They're running node managers, and then you launch your application. We have two tools to launch an application. So Apex comes with a command line tool to launch your application. You just need to have it on one node. Could be an edge node or could be any other node in the cluster. Or if you're using the DataTorrent offering, we have a visual tool with which you can call console, with which you can launch your application. And So in this particular application, it actually is showing 6 operators which are numbered 1 through 6. So you're having basically 6 operators, and each of these operators now run independently. And so here you can see, for example, how you can actually have operators in different configurations. So for example, operators 1, 2 are running on totally different nodes. 3 and 5 are actually running on the same node but as different processes. So we call that node local. And 4 and 6 are actually running as different threads inside the same process. We call it container local. And there may be the reasons why you may want to do this one configuration versus another, whether it's node local or container local, or just from different nodes. And we'll go into those details later. But all these are possible. And along with your application, we have another container, another process running called Stram, which is the master, and it's making sure everything is going smoothly. It's monitoring everything, and if anything goes down, it knows about it and it will restart things at the correct place. Um, and then the green arrows are showing the data flow. So for example, operator 1 and 2 are sending data to 3, so you can see, and they both are getting data from some external entity, so you can see that flow. You also see some MapReduce blocks here, so don't get confused. We don't have nothing to do with MapReduce. We don't use MapReduce. It is just to show that we are multi-tenant, so we can run alongside any other application that you have, and it's fine. So we won't interfere with them, they won't interfere with us. So any other Hadoop application you have, that's fine. Some more questions. Are these nodes VMs? They can be physical nodes, they can be VMs. It just depends on how you configure your Hadoop cluster. Not a problem. uh, Another question, could you please explain nodes in the context of AMS EC2 instance and auto scaling? Yes, so these nodes could be your EC2 instances, and if you auto scale and add new nodes into your Amazon cluster, uh, and they become available in Hadoop, then the operators can make use of it. They can also scale and then use those new nodes. Because we support what is called dynamic scaling. I think we are probably, in my mind and to my knowledge, the only platform that supports dynamic scaling of operators. And as it's mentioned here, we don't have any other resource manager. We're using Yarn as the resource manager, and we use HDFS for any persistent storage. So here's the application development model. So here you have a sample application that's composed of 6 operators. Uh, you have you have a first operator, which is the input operator, and it's feeding data to a downstream operator. So let's say our input operator is getting data from Kafka, and let's say the next operator is a filter that's filtering the data, producing 2 filtered streams. They're being sent to 2 different operators. This is just to show that you can have actually multiple streams split into multiple streams, and the operators are enhancing the filtered data, and they're getting joined back into another operator, which is being sent to a final output operator, which may be heading to some store. So this is just an example. Your graph. So this is an application graph, and this application graph could be however long you want. Can have hundreds of operators. Doesn't matter. In fact, we have production applications where there are there are DAGs with more than 50 operators, right? Logical operators, and each of these operators can have multiple partitions. So for example, that's the 3D effect you see in these for these boxes in the different planes. This is to show that each logic can actually run not just in one process, but actually multiple process, and the data would get divided among them, so that together they can process a larger amount of data. And so when you take when you take all these multiple partitions of all these logical operators, you may be running into hundreds of operators, and we have applications that do that. So some more questions before I continue. Is the operator equivalent of a MapReduce job, or is it converted to a MapReduce job under the hood? No, it has no relation to MapReduce. MapReduce is totally batch, right? So here there is it's its own independent system. It's a totally different model. In fact, I'll show you some of the operators. They can be any Java code you want it to be. Yeah, there's no relation to MapReduce. Next question is Apache Spark claims 100 times faster than Hadoop per challenger grade benchmark. How does Apex perform versus Hadoop and versus Spark if benchmarked? So we are a event by event streaming platform. So compared to Spark streaming, we are much faster. So Spark inherently is a micro batch system. So even Spark streaming is actually using small batches, and so when you have a batch, you automatically have latency because events have to. When you get the first event, you still have to wait for the last event of the batch to arrive before the batch can be processed. So we have people using Apex to get to where applications need latencies in the order of milliseconds, like fraud detection, and that performance you cannot get from Spark. Next question is resource manager mandatory? Yes, you need something to allocate resources. So we don't need anything special. Like I said, we just use Yarn, which comes with Hadoop. So it's a part of Hadoop. So you won't even see that, right? And then it says, is it a separate process? I think it's the same question. So yeah, again, I said, like, we don't have to run any resource manager. It's whatever comes with Hadoop. That picture was just showing you how, just the different components of your Hadoop cluster along with us. Is the topology of operators that can be specified? Yes. So you specify the topology of the operators. You can decide what code goes into each operator. So essentially, you have full control of the logic of your application. Okay, some more questions. Is Apex working with another resource manager like Mesos, for example? Not right now, but we are looking into that. And I would encourage you to go to our mailing list, users or dev, and maybe you could start a discussion there as well. So what happens when an operator crashes in the pipeline? We will get into that a little later, Baldeep. How is data distributed between multiple instances of operator inherently taken care by framework? Yes, it is inherently taken care, but if you want to have more control, you can. Again, I'll go into that in the upcoming slides. Can we pass files as stream for processing? Actually, yes. I mean, your events can be whatever you want. The piece of data can be whatever you want to be. They could be entire files. But for getting good performance, you actually want to break them into smaller pieces of data for processing. And but it's totally up to you. Does programming language make any difference in the performance when used in the operator? The platform is by default Java, so you write these in Java. However, we do provide plugs to do certain scripting in other languages. Like if you wanted to write a Python script or an R script, you could do it, or even JavaScript. Of course, when you're translating, there is a certain amount of performance degradation that you would see. But if you're using bytecode compatible languages like Scala, it's not a problem. Distributed the logic here means same logic is distributed or logic is getting splitted. So you split the logic yourself into operators. So at the operator level, yes, you are actually breaking your application logic into smaller pieces of logic, and then at the partition level, each operator's same logic is running on different partitions, but dealing with the split of the data. Okay, I hope I've answered those questions. So I'll continue. Each operator continuously emits data. Each piece of data is called a tuple, and the tuple can be any object. So it could be very simple things like primitives like int, strings, to any complex object you want, right? It could be some complex employee object. We actually allow you all that flexibility, and the serialization and everything is taken care by the platform. And this data is flowing like a stream, right? So think of it like water flowing through a pipe. So you're sending the data, and the downstream operator will get it as soon as possible. It'll do some processing, and it may emit something else, right? So this entire stream is flowing unabated through your DAG, and then your outputs are coming out. There is no batching done by the platform, right? So that gives you the a very low latency of processing. But the operators themselves have the freedom to do whatever they want. So, for example, as they're getting data, if they want to collect the data, they can. But the platform itself does not automatically does not do that and reduce your latency. And your operator can have multiple input streams, multiple output streams, and your operator can be your own Java logic. And I'll show you some examples, and I'll also build an application, so you'll see how easy it is if you're a Java programmer to write your operator. And DAG is this graph. It's made up of operators and streams. So next, we'll get into a concept of windowing. So windowing is a way of just categorizing data into these constructs called windows. This doesn't mean batch. It's not like we're batching a set of data. So when an application is running and it's processing data continuously, every so often, periodically, you want to do something, right? You may want to emit and aggregate, or you want to emit some results because you're just getting data continuously. So that's where the windowing helps. Each operator can define its own application window. It's time based, so you could have, I want a 1 minute application window or a 1 hour application window. So the platform will basically provide you some callbacks where you can do some aggregate processing. So so this is different from the event processing. So events are given to you as soon as they arrive, and you can send them out immediately, and then they go to the next operator. But every so often, if you want to do some periodic processing, you can do that as well. And the platform also uses this windowing internally, but those windows are at a different scale to do some periodic processing itself. For example, it wants to calculate stats about your operator, how much data it's processing, what's latency. It'll do that at these window boundaries. Every so often, it'll checkpoint the state. So checkpointing is saving whatever state of your operator. Think about them as variables in your operator, not data. So for example, if it's an aggregates that you're calculating, it's the aggregate you have calculated so far, right? So that in case there's a failure, it will recover the operator from the checkpoint and continue from the very next window. Not just the operator itself, but all the downstream operators will also be reset to that window so that the calculations are consistent and correct. And of course, we support sliding window and tumbling window. And this windowing concept is not batch, right? So it does not introduce any artificial latency. And all we do to facilitate this windowing is we introduce these extra control tuples, which are these really small pieces of data, every so often, like maybe a small piece of data every 500 milliseconds, versus, and it's probably a very, very, very minuscule portion of your entire data throughput. Okay, so here's an example of how an application looks like. Let me see. There's some more questions before I go there. So logic running on distributed operators should be independent, right? Yes. So your operators that's running on different operators are independent. Like they don't directly share any variables or anything like that. But of course, if the data from one is being sent to the other, if they're receiving data, sending data to each other, then there is some sort of a logical dependency, right? So it says, how is it different from Storm? So Storm, inherently, our performance is much higher than Storm because it's Storm, the each piece of data is acknowledged. So the acknowledgements are happening at every piece of data. That slows the whole processing down. But we can achieve the same level of failure recovery and processing guarantees without doing that with the use of windowing and checkpointing. So that is so it's a very big performance gain, many orders of magnitude, and the state management. So you don't have to do anything explicit for state management. Any state you have, we will recover. In Storm, you have to do or state management yourself, or you could probably use some newer versions, but still it's not very straightforward. So performance is a big key, and state management is a key differences. Will this slideshow or class recording be available? Yes, it'll be. We'll basically make the slides available on SlideShare and recording on YouTube, and we'll put the links on the meetup page. Is checkpoint same as RDD in Spark? No. So checkpoint, I'll come to it. So checkpoint is actually a snapshot of your, let's just say your current variables or current state, the information in your operator. It doesn't include data because we use an innovative way of actually getting the data when replaying the data on failure, which I'll go into, which is a buffer server, and it's a really fast operation because you typically don't have a lot of state, and it's a really lightweight operation. There's a question, but about data dependency. So maybe GT, you can explain that question again, or maybe as you can see some of the applications, as I'm explaining the application, it might become clearer to you. Okay, so here's how an application is written in Java. We do support, on the DataTorrent side, we also support assembling this application via drag and drop tool. But let's say you're doing it in Java, this is how you would write it. You implement your class and you basically you make it implement streaming application. That's the API. And you just need to implement one method, populate DAG. You're passed an empty DAG or an empty graph, and you populate it with your operators. So here we are creating a line reader, a parser, a unique counter, and a console output operator. So we're creating 4 operators, and then we are connecting them up. So we're connecting the output of line reader to the input of parser, output of parser to the input of counter, and the output of counter to the input of console, and that's it. So this is a very linear DAG. You have 4 operators just connected to each other. So essentially this in the first operator is getting data from somewhere, then data is getting parsed into words are getting counted, and the counts are being printed out. So let's say you're writing these operators, right? How does a parser look like? So what you would do is, so this is an operator that you're writing. It's extending base operator, and then it basically defines these things called ports. This is also our API. This is nothing to do with TCP/IP ports or anything like that. So the port is a way for you to receive data or send data. So input port is a way for you to receive data, and output port is a way for you to send data out. So in this case, the parser is receiving lines from the line reader, right? So on the input port, it's receiving those strings, and the process method gets called with the string, that the data that it received. So it's splitting the string into words based on punctuation and empty spaces, and then it's just emitting all the words to the next stage, right? Very simple. So let's see the next stage, which is essentially doing the counter. It's counting. So this one will receive the words that were sent by the previous operator, and it's going to count how many times each word is occurring. So it's using a hash map to keep track of the counts, and every time a piece of data arrives, it's checking the current count from the hash map, incrementing it. If it's not present, if it's the very first time the word has arrived, it's creating a new one. And at the end of the application window, which I mentioned earlier, whatever you want to configure, it's going to emit the counts. So this is slightly different from the previous operator, because the previous operator, essentially as soon as it received data, it basically broke it into words and emitted it immediately. Here, when it received those words, it didn't emit anything. It just incremented some counters, and periodically in an application window, at the end of the application window, it's emitting the word and the count. And as you can see, it's not clearing the counts. So the counts will remain, and it'll remain for the lifetime of the application, so even in case of failure. So that is the state which is automatically managed for you. Okay. So there are some more questions. So in the interest of time, I'll have to hurry through them. I may not be able to get to all the questions. I apologize, but let's see how to do. The question: how is operators different from MapReduce? Can the DAG of hundreds of operators perform more complex tasks than MapReduce? Yes, you can. The programming paradigm does not enforce strict regulations on you like MapReduce. As you can see, I showed you some of the operators. You just send and receive data, and you do whatever you want with the data. So you can have any complex processing. So you saw that. Can Apex processing include multiple data types which are in the same context in the same thread? Like you can have multiple ports, and you can receive different types of data on different ports. Yes, so it can include multiple data types. You can have any complex data type on any port. And one thing we do is the programming model to make it simple and make it error proof. Your operator itself runs in a single thread. So your logic is running in a single thread. Even when you're receiving data from multiple ports, you always can be sure that you only one thread is running your application code, your operator code. So which means that you don't have to worry about concurrency problems. If you want parallelism, yes, you can have multiple operator partitions, right? And these operator partitions can be container local, or they could be running in different containers. So that way you have multiple instances of your logic running parallelly, processing different pieces of data. Next question: is it in-memory operation? Yes, it's all in-memory computation. Sensor-based stream. I did not understand the question, but I'll continue. Logic running on distributed operators should be independent, right? But what about data dependency? Yes, so you can. I mean, your operator can be emitting. So your operator would receive some piece of data. It can do some transformations on it and emit a different piece of data. And yes, then there is a dependency. And if you want to do things like lineage, we do have solutions available in DataTorrent on how to track how a piece of data changed. But yes, of course, the output data that you send, would have some relation to the input data that was received. Traditional SQL data sources. Yes, we support your traditional. You can read from traditional RDBMS, JDBC sources. You can write to them. In fact, today's today's application that I'll build later, I will actually write to a MySQL database, so you can see that. File-based data, yes, you can read from file-based data. We have operators to do that and do it very efficiently. Like I mentioned, we also have an ingestion application that you can check out that does that. If there are no aggregation, how do we preserve state using checkpoint? So checkpoint saves any state, so it doesn't have to be aggregations. Any variables that you have in your operator that are not transient will be saved. Okay, so it doesn't have to be aggregations. Some more questions. I think let's continue. Otherwise, in the interest of time, and maybe some of them will become clear as I go to the next slides. Okay, so let's look at partitioning and unification. I think some of your next questions are about partitioning and unification. So this is the core it's a core concept that's supported in the platform, because to process big data at large scale, you have to partition. I mean, you need to have multiple instances of your logic running, each of them processing subsets of your data, right? So here on the left, I have an application which you built with 3 operators, 0, 1, and 2. And in reality, in practicality, you may actually need multiple partitions. So in this case, operator 1 is partitioned into multiple instances, and the data from operator, which is number 0 here, is actually being split, right? Now, how this partitioning happens and how you can control it, I'll come to next, right? But here it's just showing you that it is possible. So your question could be, hey, why are you partitioning 1 and why are you not partitioning 0? Yes, you can partition any operator. That's not a problem. Here, I'm just showing it as an example. 0 may be an input operator that's very lightweight. All it's doing is getting data. But 1 may be doing heavy computation, right? It could be doing parsing or doing some complex processing. And to be able to keep up with 0, it may actually need multiple instances, right? So to give you the low latency. So essentially you can partition each stage independently. And then when you partition, there may be a need to unify. So let's say 1 is performing a mathematical operation like average. So maybe it's getting a whole bunch of keys and it's performing average. Now, when you split into multiple partitions and each partition is receiving a subset, each of them will compute the averages of the subsets, but you need to combine them to get the final average, right? So in that case, you need what is called a unifier. So we support the notion of a unifier. Uh, it's inherently supported. For example, when you have for an operator, when it gets partitioned, you can supply a unifier, and the unifier itself will run as another operator. It's a construct that's natively supported, and it'll receive the results of all these partitions, and it can again unify it according to whatever logic it wants to do. On the right side, you see more complex partitioning scheme where you have, let's say, 4 operators, and 1 and 2 are both getting partitioned. So in this case, uh, if we continue, if we extend the logic that we were talking earlier, and we put a single unifier between the first and second stages, that could bottleneck, because you have all the data coming into one unifier and then getting split into the partitions of 2. So we support what is called an n by m or m by n mechanism, where each downstream partition has its own unifier and it's getting its own subset of data directly from the source. And this gives you a much higher network throughput and performance. And again, the output of 2 is getting unified. Okay. So one question is streaming versus buffering. I want to merge tuple A, tuple B, and tuple C. You can do that in the operator. For example, our join operators do that. How does shuffle happen? So there is internally so your operators are running inside our platform code that runs along with your application. It's called a streaming container, and in that there is a buffering mechanism called the buffer server, which is used in which is used between inter-operator communication and all the in the networking side, which you don't see when you're writing operators. And it also helps in failure recovery, and shuffle happens in that mechanism. And I'll explain how data gets actually split across the partitions in the upcoming slide. So question of how is Apex different from MapReduce? We are full in-memory processing, write your own logic, multiple stages, no more 2 stages, send any data you want, write any business logic you want, just supports many different types of applications, much faster. Yeah, those are the differences. Looks like window size will have an effect on performance and memory usage. Does the platform auto tune it? So window size will typically does not, because window is not batching. You are getting the data continuously. Think of window just like a periodic callback that you get where you want to do something. Of course, if you're holding the data or doing something, the data you're doing something, you're keeping aggregating data in memory for the entire length of the window and then clearing at the end of the window. Yes, it can affect memory usage, but then we do have support for large state, where essentially we do a combination of in memory and disk caching. You can find those operators in our library. And yes, but you have a choice. Each operator you can set any window size you want. Okay. Right now I'm not able to answer all the questions because of the time constraints. Question similar to Unify: do we have a splitter? Yes, splitting happens automatically, and you can control how the splitting happens, and we'll go into that next. Could you talk about the windowing checkpoint feature? If that coming down, that's fine. Yes, I'll talk about that. How it will be useful to have with 2 unifiers for partitions, as same with data with transfer to 2 queues like that. So think about it like this, right? So let's say each of these partitions of 1A, 1B, 1C are outputting, let's say, 10,000 pieces of data, right? And let's say, so essentially overall there's a 30,000 pieces of data per second, let's say, is coming to the unifier, and the downstream are, let's say, taking data equally, and they're getting 15,000 pieces each. Now you have a single unifier that's now getting 3 times the network data, right? It's getting the 30,000 pieces of data. But in the other case, you are actually each of those 2A and 2B network cards, or the network throughput, is only receiving 15,000, right? So um, when you're reaching higher throughputs, where you're maxing out your network bandwidth, you'll bottleneck with a single unifier. Of course, if you want the single unifier, we still support it. Um, you can, that's an option as well. So more partitioning schemes. So this is a unique partitioning scheme we support called parallel partition on the left side. Um, so here, let's say you don't want to shuffle, but you are actually um, processing, you're doing multiple layers of processing on the same piece of data. For example, you may be parsing a line, then you may want to do some filtering, and you want to do some enhancement, and you just continuously doing that on different pieces of data. So and there's no relation between successive pieces of data. So you can run a parallel pipeline where the partition of 2A partition 2A receives data from 1A directly, and there's no shuffle. And on the right side is another unique thing we support called cascading unifier. Suppose you have a large number of partitions, and the results needs to be unified, um, and because they have a large number of partitions, they're producing a lot of data that the unification cannot be done in a single unifier. It'll basically bottleneck the whole system. So we can introduce a series of stages of unifiers, and each stage deals with a small number of partitions, and it unifies that, and then the next stage will unify the result of the unifiers, and so on. So, and in this case, the platform acts like a smart system. All you do is specify how many partitions you want to unify in a unifier, like in this case 2, and it figured out that it needs to create 2 stages of unifiers. In the first stage, there needs to be 2 unifiers, and the next stage there needs to be 1 unifier. So it'll figure those things out. All you need to do is specify how many unifiers need to be unified, how many partitions can be unified in a single unifier. So next is dynamic partitioning. One question, in the previous question, does 2A, 2B have to be the same logic with parallel processing? Yes, so all partitions will run the same logic. Same. So 1A, 1B will be the same logic. 2A, 2B will be the same logic. That's always true with partitioning. So the logic will be the same. It's just they're running in multiple processes, receiving different pieces of data. Okay, so dynamic partition, this is another unique thing we support. This is where the partitions can change dynamically as the application is running based on your choice, how you want to, when and how you want to change the partitions. And they do all this without losing data or causing doing any inconsistent calculations. So you have a control with the Apex API to provide what's called a partitioner, and the partitioner can decide when to partition and how to partition. And we provide some default implementation of the partitioners that you can use right out of the box. So here in this case, let's say you have two partitions of 1, 2 partitions of 2, and then you have a third operator 3, and suddenly your load increased, right? You suddenly start getting more data in from the external system. I'm just depicting them with longer arrows. So now let's say your stage 2 is not able to keep up. So now you can partition from 2 partitions to 4, right? And as they're processing, now there's more load on 3 as well, and then 3 can also get partitioned. So you can determine how and when to partition in a programmatic way, or by using the default partitioners that we have. We provide a throughput based partitioner. So based on how much throughput you can set a ceiling throughput, and once the ceiling throughput is crossed, it will partition into more partitions. And one more example is our Kafka operator. So our Kafka operator, input operator, can detect how many partitions are there for the Kafka, and and uh, and it can basically create as many number of partitions so that it can consume at the maximum rate from Kafka. So if your Kafka side has 4 partitions for a topic, we can automatically create 4 operators. You don't need to know. So you just point it to the topic. We'll create 4 partitions, and then we'll consume parallelly, right? The highest speed possible. So next question that came up quite a bit: how are tuples? How do the tuples? How does the data get split, right? So our default way is to use the hash code of the data. So it can be, as I said, it could be data, could be simple things like primitives like integers or characters, or could be any complex object or even strings or anything you want. So we take the hash code of that and use the hash code for partitioning. So here, let's say in your downstream operator, it has 4 partitions, then and your upstream operator is sending some data. We'll basically look at the last 2 bits of the hash code, and based on those last 2 bits, we'll send it to one of those 4. Now, sometimes hash code is not something you want to use. You want to use some key in the data, like maybe it's an employee object and you want to use the employee ID or something like that as a key to split the data. You can do that. We provide a way. It's called a stream codec. You can easily define a stream codec, and you can pick what you want in the object. It could be a combination of keys. It's again it's Java, so you can write whatever code you want. You're given the object, and you can generate your own hash code. Uh, and uh, and uh, and also you can also control the serialization. If you want to do your own serialization and deserialization, you can do that. It's not needed, but if you want to, you can. Some more questions. Are the operators intelligently deployed on nodes, or are they deployed based on configuration? The operators are deployed automatically on the nodes. You basically just create the DAG. That's it. And you can say how many partitions you want to start with, and we'll ask Hadoop for the resources and deploy the partitions. And if there is dynamic partitioning, we'll request more resources and get it. Is dynamic partitioning configurable or on demand? You can configure it. So it is on demand. So you don't need to. You're not using the resources when you don't need them. And however, you do make a provision for it when you're actually writing the application. You configure it accordingly that you want dynamic partitioning, and then at runtime we'll get the resources when it's needed and release them. That I think comes to the next question as well. Does dynamic partition has to be programmed? So if you're using our dynamic partitioners, you just set them, right, and they'll do it. But in some cases, dynamic partitioning requires a partitioner to be written, especially if you have state, right? If you have state in your operators and you're going from 2 operators to 4 operators, you may need to distribute the state from these 2 to the 4, and that state is very specific to your own logic. So, but we provide an API where you can do that in a correct way, and you don't lose anything. Okay. Does it also support scale down? Yes, it supports scale down. What is the default serialization? We use Creo. However, we also provide other options, Java, and then you can use Java serialization as well. If you want to use yours, you can plug in with the stream codec. Can Apex dynamically scale up and down based on performance requirements? Yes, we have throughput based scalars, and we have latency based scalars out of the box, and you can also write your own as well. Okay, and then we support more custom splitting. I should probably call this splitting, not partitioning. So for example, you want to do something fancy where you don't actually want to split the stream, but you want to send the same stream to all the downstream partitions. You could do that because we can take the hash code, and we basically apply what is called a mask, and then you can basically set the mask as 0, and then essentially everything will map to the same result, and it'll go to all the partitions. This is very rarely used where you need it. Let's say you want to you have an operator that receives something like a query, and you want to send the query to all the partitions. You can do that. Again, this is just to show the flexibility, not that you'll probably use it in real life. In real life, you're almost always splitting the stream. Okay, next we come to fault tolerance. So what's fault tolerance? Like we talked about, your DAG is running, your nodes can go down, your operators can go down. We have to be able to recover correctly and recover automatically. So the way this is done is the core pieces are the operator state is checkpointed periodically, not the data. And then when, in case of failures, the operator is restarted from the previous checkpoint. So by default, checkpoints are happening every 30 seconds on the operator, but you can again configure that. So when an operator goes down, worst case, it's going back to an image that's 30 seconds back, not something at the beginning, right? So you you can catch up fairly quickly, and then so it basically recovers to the checkpoint window, which is basically maximum of 30 seconds behind, and then it will receive data from that point onwards, from the very next window onwards, not so that it's in the correct state and it's receiving consistently the data it needs to receive. And the downstream operators are also automatically reset to the checkpoint. So, and the state is also reset to the checkpoint. So everything is being computed consistently and in an idempotent fashion. And checkpointing happens asynchronously and distributedly by default. And when we are storing the state, we are using HDFS to store the state. Even that part is configurable if you want to store the state outside. And as I mentioned, state is not data. It's typically very small. And how do we detect whether an operator has failed? Sometimes Jan tells us, but we also have our internal heartbeat mechanism. So if an operator doesn't report to the application master periodically, then we know it's basically dead, and we'll recover it. We also have a buffering mechanism to ensure replay of the data from recovering checkpoints. So when an operator basically gets recovered to a checkpoint, it needs data from the very next window, right? So that data is actually available in a buffer in the upstream operator, which we automatically do. So we just replay from that buffer. So that's how the operator is able to get the data. One question, is my understanding correct? Each partition is a separate thread that runs the code written for each operator on a given data slice. So each operator is running as a separate process or a separate thread, and it is receiving data continuously, the sizes of data from that is being sent by the previous operator continuously, right? Can we store checkpoint to any NoSQL DB? Yes, you can store checkpoints to any external store. We also have an implementation which stores to Geode, which is an in-memory grid, in-memory data store. So people have written those as well. Does operator ensure the ordering of events on recovery replay? Yes, that's correct. On recovery, the operators are replayed exactly in the same order. The events are replayed in the same order, and you don't lose any events. How granular should the operators be? Does the granularity of operators affect performance? They can be what you want it to be. As I said, you can ideally, if you want to get the maximum performance, you want to break it down to as small as possible, so that you get the full pipelining benefit, right? So you can be processing more pieces of data. Your entire pipeline could be processing more pieces of data. Okay. Also, one more point is the application master state also gets checkpointed. So in case, because application master is also running along with your application, so it could also go down on a node. So if it goes down, we'll recover from the checkpoint. So in that case, Hadoop just restarts the application master, and then we recover the application master state from the checkpoint. So you don't lose anything. The question is, does the platform automatically decide when to place the operators in the same process or not? I will come to that next. Is the checkpoint stored globally for each worker or accumulation of all workers? Checkpoints is stored separately for each operator, but it's stored under the same HDFS folder, but it's configurable as well. But each operator has access to its own checkpoints. You can quickly recover in case of a failure, and it's not parsing through some big file. How does application master restore? So application master stores its checkpoint. Application master is restarted by Yarn. So Yarn only guarantees that. So it only restarts the application master, not all the containers or all the operators or anything like that. And then application master will basically go to HDFS, get its state, recover itself. Then if it needs to recover any operators, it will recover them as well. How does master get notified in case of failed operators? Two ways. It gets Yarn notifications because it has a listener that's listening to events from Yarn, or we have our own heartbeat mechanism where the operators are pinging the application master periodically, because they're anyway conveying their stats and those kinds of information. And also they are receiving information from STRAM if there are any dynamic changes, like changing properties which we support dynamically at runtime and so on. So there's this like a small periodic heartbeat that goes on. So if the master doesn't receive the heartbeat, it can determine that it's gone down as well. What are the different data sources that's supported? We support different types of data formats, different types of input-output connectors. I went through some of them earlier when talking about the operators. I'll go through them again later on as time permits. Okay. So processing guarantees. So what? So the recovery that I described to you before is what we call at least once. So what it means is the operator gets recovered to an earlier checkpoint and it gets data immediately from the next window. But the reason it's called at least once, so it's still it's consistent processing. It's no loss of data and so on. But the reason it's called at least once is because in the previous run you had processed, you may have processed some of the data, and when you recovered, you're processing some of the data again. That's why it's called at least once, not that it is processed more than once in the same run. And essentially we guarantee that no messages are lost, and this mechanism is actually suitable for most application. And we actually can do end-to-end exactly once with this scenario. And we have written blogs and we have done webinars before as well. And you're welcome to look at our website and how we do that. So how do you do end-to-end exactly once? So let's say, for example, you're writing to a data store like a database, or let's say you're writing to a file. How do you ensure that you don't write data multiple times in case of a failure and recovery? Even though in recovery it's reprocessing a small amount of data, how do you ensure that you don't write multiple times, right? So we have ways of doing that. Our operators, we have pre-built operators that do that, and and you please we have blogs on how that happens. The next thing is at most once. So some applications actually, when they fail and they recover, they don't care that they don't need to process all data. For those applications, you can set the recovery mode to be at most once. It's configurable. That means when the operator starts, it's right away starts. When it restarts, it right away starts processing new data. No, it doesn't reprocess from the checkpoint. So exactly once. So this is what I was talking to you about. So exactly once, we can do end-to-end exactly once with the platform doing at least once recovery, and with stateful recovery. So for example, if for example, if a Kafka input operator goes down, when it comes back up, it'll have the last offset it read from. And with idempotency, we can basically ensure that we are only writing once. An example is, let's say you have a file output operator that's writing to a file and it suddenly died. So when it comes back up, it'll come back to the previous checkpoint and it'll have the file offset at the checkpoint. So it'll truncate the file back to that offset and start writing again. So which guarantees that no data is lost and no data is duplicated. So we use things like that, techniques like that, to basically ensure end-to-end exactly once. Stream locality. So this is, I think, somebody basically asked, how do you ensure that where you're putting the operators? So by default, operators are just put into different processes. So we basically ask Hadoop for give us containers, and Hadoop allocates a container and we put it in a different process. But you have more control. You can by using properties on the streams, you can actually put operators in the same process, put them on the same node. You can ask them to be put on the same node. You can ask them to be put on the same rack, or even same thread, where they become like successive functions. So the thread local and container local are something we provide. So that's something that modes that we are doing internally. When node local, when you ask for operators to be on the same node, we are asking Hadoop to give containers on the same node, and we're trying to put it on the same node. The rack is similar, but the other modes are actually, we are getting one container. For example, container local, we are getting one container and running them as different threads in the same container. So why are these needed? So there are advantages to each of them. So if it's in the same rack, that means typically it's on the same network switch. So you may have cases where you don't want, and these operators are sending data to each other, right? You don't want the data to go on to another switch. You may want to put it on the same rack, same node. maybe there are two operators that are sending a lot of data to each other, and by them being on the same node, that data doesn't even get onto the network. It just gets routed through the local loopback. And container local, in this case, the operators are directly exchanging pieces of data through a queue, so there is no serialization required, much faster. Thread local, basically in this case, you have an operator that's maybe that rarely does something. So for example, maybe there's an operator that basically is looking for some alerts, right? It's looking for some error conditions, and there may be an operator that might send an email when there is an alert. Now that's a very rare occurrence, right? You may not alerts may not be may happen very rarely. So you can put the operator that sends an email along with the operator that checks for the alert in the same as a thread local, because because one operator is rarely being the operator that sends an email is rarely being used, so it doesn't have to consume a lot of resources. One question, is checkpoint happening for each record it's writing? No, checkpoints happening every 30 seconds by default, which is many windows. So, and then it's not writing data, it's just storing the state. Let's see. One question is, how does consistency is ensured? So the reason consistency is ensured is when an operator fails, it is recovered to a point in time, and then it gets the very next piece of data that it had received before at that point in time, and followed by the same pieces of data that it had received before. It's almost as if we are rewinding and continuing and replaying and doing exactly the same thing we did before. That's how consistency is ensured. Checkpointing happening every 30 seconds, not milliseconds. Yes, that was the question. Okay. All right, let's go to the next one. Okay, so now we come into some of the, these slides just talk about some of the features that we provide in DataTorrent on the enterprise edition on top of Apex. So earlier I showed you a DAG, how you would build your application in Java. Here's our graphical builder where you would drag and drop and to create your application. So but you need the operators. So you have the operators on the left side, you drag and drop and connect them, and you can specify properties for the operators on the right side, and you can deploy the application. And this tool that you see is our UI tool, which has all the, which is everything in one. It has our assembly tool. It has our application monitoring. So here you're seeing an ingestion application. That's a DAG that was built out. It's actually, this is basically a DAG that was built to bring data into Hadoop. If you're trying to ingest data from an external system into Hadoop, or you're doing Hadoop to Hadoop copy, you can use this application. We also provide this application along with our enterprise edition. So this is the monitoring tool. It's showing you, for example, the logical flow of your application. It's showing you, how much memory it's using overall. It's showing you how many operators. On the top right side, it's showing you the important events. And if you scroll down this window, which I cannot, it's a screenshot, you could also see for every operator its stats, like how much data it's processing, its throughput, its latency, where it is running, and so on. Here's the physical view of the same application. So it's the same logical application, but there are multiple partitions of block reader and writer. So here in the physical view, you actually see them, all the partitions. There are 4 partitions of block reader and writer, and and this is what we call the physical view. And finally, our real-time dashboards. So if you want to actually basically, let's say your application is producing some output data, and you want to actually visualize the data in real time without I mean, you may want to store it as well, that's fine, but you want to directly visualize the output of the data immediately in a dashboard, without having to go through a store all the time, and because you want the data now, you want to visualize the data now. We couldn't find many tools that did that actually correctly, and it could handle high speed data. So we built our own real-time dashboards as well, and we support various widgets here. So I think one other question was, is the checkpointing interval configurable? Yes, it is configurable. You can configure it on a per operator basis as well. Okay, here are some resources. Basically links to our to the Apex website. If you want to subscribe to the mailing list, you want to download it. You can please follow our Twitter. We frequently post tweets about our meetups and big events that are happening. Like when we went top level a couple of weeks back. Facebook, a meetup page to keep track of the events. And if you want to use DataTorrent and you want to try out the Enterprise Edition, um, you can. We have a startup program, and it's free. It's very minimal cost. I think it's almost free. You can go to this our web page, go to the startup accelerator page, and and then sign up and get it and use it. If you're a startup, we want you to try it for free. We know startups uh, you know cannot pay a lot for license and so on, so you can use it for free. And below is a map you can see of our different meetups that happen. We have quite a presence in US, and then we have a growing presence in India as well. And if any of you want to do your own Apex meetups other places, feel free to contact us, and we'll be more than glad to help you out. Um, so what is the tech stack being used in real-time dashboard? It's actually Angular, and then WebSockets, so that data can be streaming continuously, and it's and then we have a pub sub server at the back end, and the operators can publish data, and the dashboards can receive data. And we are very soon we are going to do a meetup where we're going to talk about how you can build your own widgets and add it and so on. So somebody says, cool, thank you. How does Apex know the list of operators configured in our application? Does it scan through annotations? How does it start with my first operator? Okay, good question. So you add your operators to the DAG, so that's how we know. If you remember that application. How do we know the first operator? Because the first operator is the one that implements an extra interface called input operator, because it doesn't have an input port. Your first operator does not have an input port, right? It only has an output port. It's only sending data out. It's getting data from somewhere else. So that's how we detect it. Um, Questions. Okay. Apex versus Spark versus Flink. I covered Apex versus Spark. Flink has similar streaming philosophy as ours. We actually differentiate from Flink basically at a feature level. Of course, we have a big library of operators out of the box that are ready to use, that you may not have with Flink. Also, we can recover much quickly from failures, because when there's a failure, only the operator and its downstream get recovered to a checkpoint, because we have a buffer server and we can immediately replay the data. In Flink's case, the entire DAG is reset, and this has been a critical thing for some very low latency processing applications, where they just can't reset the entire DAG. And of course, dynamic partitioning, and at a feature level, yes, but philosophically they're also a streaming platform. You can okay. I see it is similar to big streams. I apologize, I don't know about big streams, so I cannot. Somebody congratulating me for the talk. Thank you. How long is the startup accelerator license valid for? I would encourage you to go to the website. It's very, we want to make it very easy for the startups. I think there's very few restrictions. I think it's a very open type of thing. It's welcoming type of thing. I don't know the exact details, but yeah, please go to the website. So a use case that would be better for Apex or conventional MapR or Spark, definitely where you are trying to have where you have low latency processing, and think about if you have latencies in the order of seconds or milliseconds, definitely. And if when you have when you have a large state to manage, and you don't want to do this explicit data and state management and synchronization yourself, you just want to write your code the way you would write it if it was a single process, right? As you saw, the code is just standard Java code. Like I showed you the counter. There was no difference. That's how you implement a counter in standard Java. You just write your logic the way you write a Java application. The logical physical view of the DAG both need to be defined by the user. No, just the logical view. Physical is automatically generated, but you can determine its destiny. So you can say how many partitions you want. That's all you say. Or if you want to use dynamic partitioning, which dynamic partitioner you want to use, and then the DAG will get created, the physical DAG. Thanks for the presentations. How many production developments are using open source versus enterprise edition version? Um, so sometimes it's difficult to know how many people use open source version because they sometimes don't tell, right? We have heard of a few big firms that are using the open source. Enterprise, we have quite a few customers across the you have people in the Fortune 10, Fortune 50, big companies, banks, industrial space, ad space, and even in IoT space. So people are using it. Okay, so now I think I'll spend half an hour to quickly build an application. I think so, it'll be a little change of pace, and it's going to be some Java development. But if you don't know Java much, I think I'll still explain what I'm doing. So hopefully you can follow. There won't be a lot of complex stuff. So let's just get on with it, right? Um, and feel free to continue to ask questions. And then I'll start building the application. So typically, we provide you an easy way to get started building your application. So we have a default project generator which generates a default template project that you can use right away. So I have a little bit of a cheat sheet that I'll use to copy because I don't always remember these commands, and I've already collected it from documentation. It's all in our documentation. So we have a Maven archetype that will generate a template project for you. So here I'm creating a project. I'm calling it Meetup app. I'm giving it some group ID and an artifact ID. If you're familiar with Maven, this is how you identify a project. So I'm just going to run that. So it says yeah. I say go ahead. So now once I do that, it would have created a project with a folder of the name of what you gave for the project, Meetup app, right? And it creates an application and it creates a Maven project for it. So it's all good to go, ready to go. So I can open this in my IDE. So pick any IDE you want. I use IntelliJ. You can pick anything. They all understand Maven projects. So here I'm going to open. It's a different one. So I'm going to open the Meetup app. So as you saw, I didn't have to create any project or anything in the IDE, right? Because it's Maven, it'll understand it. And right away it opens it, and you can see the project structure. So we already create a simple application here. Think of it like a equivalent of a hello world, right? It has two operators. It has a random number generator, and we created the random number generator right here. So you can see what we did. Very simple, generates a bunch of random numbers, and a console output operator, which is actually coming from our library, which we have imported. You can see that it's coming from our library, from the library of operators. And all it does is print whatever it receives onto the screen, the system out, and system outs typically go to a log, a standard out file in the Hadoop, and we'll show how we can access that. And then we're just connecting the two operators, right? So we created this so that you have right away have something to start with, and you can modify this to create your application. And a few more things about the project structure. So you see a resources folder here with some properties XML. So you can specify properties for your operators, things like URLs and locations and so on, and that you don't want to hard code in your code. And then this is the interest. We also provide a test. We show you a way to test the application right here in your IDE itself, even before deploying to Hadoop. So the same application that you created here, with a little bit of glue code in JUnit, you can actually run the same application. You can see it's the same application that was created. So you can run it right here in your IDE, and it's going to run it, and it's going to print the output here because it's a console output operator is going to print. So you can see the data being printed. And normally your application will be running continuously, but we are only running for 10 seconds here. So it'll stop after 10 seconds. So what this gives you is an ability to debug your application with all the rich set of tools that your IDE provides, right? All the debugger and breakpoints and all these things right in your IDE, even before you deploy the application on your cluster, right? So that essentially basically, you can catch a lot of the logic errors and fix them right here, right? And it's running the same code. It's running the same operators. It's basically using the same backend. It's just that it is not talking to Hadoop. That's all it is. So yeah, so it's a good representation of how it would be in runtime. So now we'll change this application and we'll write our own. So I'm going to delete this operator because I'm not going to use it. Okay, delete anyway. Then I'm going to delete this existing DAG that was created, and I'm going to create my own. So what I'm going to do now is actually I'm going to read some data from streaming data from Kafka. I'll read in data from Kafka, which would be line by line, break them into words, do a count on the words, and write the output to a database, right? So for that, I would need to talk to Kafka first, right? So we have our Kafka operator in our library, and then we'll include that. So first, I'll include the dependency in the POM XML so we can use those operators. And then I also want to write to MySQL, so I need to have the MySQL operator as well. So I'm going to go here and add our dependencies, which basically bring the library that has the connectors, Kafka, and the MySQL, and also the MySQL driver and so on. And so this is standard Maven stuff. I'm going to the dependency section, and I'm going to add dependency here. So this is using an older version of the library. I'm going to put a new version in as well. So you can see I added a newer version of the library, which is 3.3, and I've added the Kafka. So the Kafka connector is in our Malhar contrib artifact. Then added the Kafka jars themselves, the Kafka clients themselves. Then added the MySQL, and these are the old stuff. And then what I'll also do is I'll just give our application. So our application gets wrapped into a package. I'll give it a name. I'll call it my meetup application. Let's call it meetup application. Give it a little bit of description. My first application. So you can actually have multiple applications in a single project. So you can name the individual applications yourself. So I'll call it meetup application as well, because we're just going to have one. And if you have multiple applications, you get to choose which one you want to launch. So now we'll start creating a DAG. So the very first is I'm going to create a Kafka operator because I'm going to read data from Kafka input. So I'm going to it's an operator in our library that we just included. So it's called Kafka single port string input operator. It reads data from Kafka and brings them as outputs them as strings. So I'll call it. So I'm going to add, and then you can give it a friendly name. So in this case, I'm just going to call it input. So this is how you add an operator, right? So this convenience function creates a new instance of the operator class and returns it as well and gives it a friendly name. So next what we are going to do is we want to take these lines and then we want to parse them and then break them into words, right? So I'll write an operator for that. Now some of these operators already exist in our library. I'm just writing it so that I can show you if you were to create your own operators how easy that is. So I'm going to call it parser, and I'll extend base operator. This is very similar to the code I showed you in the slide. Okay, and I'll define an input port. So it's going to take strings because the Kafka operator is going to emit strings, right? And then it's telling me I need to import it. Sure. So you can define as many inputs you want, and then you just connect them up when you're connecting them in the DAX. So I'm just created I defined one input port, and then the input port has one abstract method called process. So whenever new data arrives, this process method is going to get called, and it will have the string that just arrived. So I'm going to break this into words. So I'm going to split the string, and for splitting, I'm going to use a regular expression. Since I don't remember regular expressions and I'm not terribly good at it, so I'm just going to copy it from, because I have the regular expression I've kept. So this basically breaks the words at not just spaces but at punctuation boundaries as well, right? Then I'm going to loop through the words array, and I'm going to emit the words. Now to emit it, I need an output port. So I'll go ahead and create an output port as well. Again, the output are going to be words, which are also strings as well. So I define them of type string. And as I said, these output port and input port, basically they take any type, right? So you can basically emit any object you want. But when you're connecting an operator to another operator, the types of the input output port of the upstream and the input port of the downstream should match, and we check that. Okay. So now all I'm going to do, I have the output port. I'm just going to use that to emit the word. That's it, right? So the only thing the API asks you to do is to use input and output ports to get the data and send the data. Whatever else you want to do is up to you, right? So it's a very little restriction, or very little thing that the very easy to use unobtrusive API. So now I go here and then I create the parser. Oops. Okay, and then I'll connect them up. So I'm going to call, so now I'm going to add a stream. So I'm going to connect the output of the Kafka input operator to the input of the parser. And since the Kafka operator is emitting lines, I'm just going to call the stream lines. Okay. So next what are you going to do? So let's say now we have the words, right? So now the parser is emitting words. Now I'm going to take these words and I'm going to count how many times each word is occurring. So I'm going to create a counter, right? So sure, I can create a counter that basically takes input strings and counts them, but I can actually make it a little more general. I can make it a generic type T, so that I can use the same counter no matter what you're sending me. If you're sending me integers or strings or any object, I can basically count them. So I'm just going to make it a general operator, so it's reusable, right? And for that, I'll say my input port, I won't fix it anymore. I'll just say give me any type T, right? So again, it's telling me, hey, do something when you get the tuple. So it's asking me to implement the process method. So what I'm going to do is I'm going to keep a hash map of the counts, and then I'm going to increment the count each time data arrives. So I'm going to keep a map of the counts for every tuple. Oh. Okay. Sorry. Okay. Keep the counts. So I'm typing quickly. So okay. So what I'm going to do is whenever a new data arrives, I'm going to get the current count. Right? And I'm going to increment it, right? But if it's not there, I'm going to create it. So if there's no count already, so if it's the very first time you're receiving a certain tuple, I'm going to create one, and I'm going to put it back into the map. So this is standard Java stuff, right? Or any programming language stuff. And I'm going to increment the count, right? So that's it. Now, essentially here, what's the difference between this and the previous operator? The previous operator, basically, as soon as it got a line, it split it into words and emitted output immediately. But here, I'm not emitting anything yet. I'm just getting the data. I'm just adding it to my map of counts. Now, periodically, I will emit it. So at the end of every application window, I want to emit the count. So this operator is slightly different from the previous one. So what I'm going to do is at the end of the window, I'm going to output the counts. So periodically, essentially, that gives the result of periodically emitting the counts. So to do that, I'm going to, because I extended the base operator, I have a callback when the window ends. It's called end window. So I'm going to override that. So at the end of the window, every application window, the end window is going to be called. So at that time, I'm just going to loop through these counts, and then I'm going to emit the output. So I'm just going to loop through the map. Right? And I will emit it, and then I'll emit it as a key value pair. So let me create an output port. And I'm going to output a key value pair for every tuple, right? So I'm going to emit a key value pair of the tuple and the actual count, how many times it occurred. So that's my output port. And so here I'm just going to emit a new key value pair of each for each tuple and its count. Okay, that's it. Now what I'm not going to do is I'm not going to clear this map. So the counts will be cumulative. So it will keep on growing, and every window you're getting the new values for the tuple counts. Which means, let's say I don't have any data in a window, and window is still going to get called, and I'm going to still output the old counts. I don't want to do that. So I only want to output the counts when something has changed. So I'll use a Boolean variable saying some data was available in this window, right? So whenever data arrives, I'll just set it to true. And in the end window, what I'm going to do is only if something was available during that window will I output the count, and I'll reset the available back to false at the end of the window, right? So very simple, standard. Again, it's very natural, the way you would build any logic. So now that we have the tuple counter, I'm going to go back to the application. I'm going to create the tuple counter operator. I'm going to instantiate it. And now here specifically I'm using it to count words. So I'm going to create it of type string. Call it counter. So somebody asked me, do the ports have to be marked public? Why? Because we are basically using it here to refer to them when adding it to the when creating the streams. So here I'm going to create the next stream, which is connecting the parser to the counter. So the parser is sending us words. So I'm just going to call it words. Take the output of the parser, output port that we defined in the parser earlier, right? And I'm going to connect it to the input port of the counter, right? And then last operator, what it's going to do is it's going to take these counts that it's receiving, the key value pairs, and it's going to write it to a database table. So I have a database table here. That has, it's a very simple table. Oh, I mean, I need to connect again. It's been, so it's a table called word count. So it has just two columns, very simple, a word and the count. And right now it doesn't have anything. It's empty. So I'm going to send the word and the count. I'm going to write it to that database. So I'm going to create an output operator. So I'm going to create a JDBC output. Now again, you don't have to write any JDBC code from the scratch, because in our library we already have a JDBC operator. It has all the logic, the JDBC logic. All it wants you to do is tell it how to map the data to the columns. So I'm going to just extend that the library operator, which does all the hard work for me, right? And it's asking me to specify what type of data it's going to receive. So remember the unique counter, tuple counter, was basically outputting a key value pair. So I'm going to say that you're going to receive a key value pair of strings and integers, which is essentially the word and its count, right? And And the ID says, you know what, finish. So there's some methods that you need to implement. So let's see what those are. So two methods. First one asks the SQL statement that you want to use, and the next one asks to populate the prepared statement with the data from the input tuple. So this is standard JDBC, right? So again, I'm not writing any JDBC specific code. All that is being handled by the library operator. But if you wanted to write one of your own from scratch, you could do that as well. So again, SQL, I have it here. I'm not going to type the whole thing, so I'm just going to take the SQL. This is essentially doing an upsert. Oops. Into the table. So it's basically inserting into word count the values, and each time for every tuple, I have this prepared statement that I'll populate, and then this will get called by the JDBC code that's in the abstract operator. So I'm going to set the first parameter, which is an integer. So this is, if you have written JDBC code, this is like standard stuff there. So the first one's actually in the word, which is an int, which is a string. Sorry, and the second one, and in JDBC the numbering starts from 1, so it's 1 and 2. So that's it. We have the output operator as well. So I'm going to go here and instantiate it. Okay. Then I'll just add the final stream, which is to connect the counter to the JDBC output. So you take the output of the counter, which is the one we had created here, the output port with the key value pair, right? And I'm going to connect it to the input port of the JDBC operator. And we didn't have to define it because the abstract operator already has that input port, the one we just extended. And the same type T that you specified became the type of that input port. So at this point, we are done with the application. We just need a few properties. For example, for Kafka, we need to tell where the server is. For MySQL, we need to tell where the server is. So I go to the properties XML. I'll clean out the old properties that are already there, because these were for the test application that was generated, right? And then I'm going to copy over the properties that I already have prepared, so I don't have to write it in front of you guys and waste time. So you can see these properties are actually specifying the properties for these operators. So for example, for the Kafka operator, we called it input, right? That was the friendly name we gave. So we are basically referring it to by the same name, and then we are we are basically setting a value for the topic property. So we are saying that the Kafka topic is meetup, and the Kafka zookeeper is this node which is on our lab in our cluster. Then for the output operator, which is the JDBC operator, right? We are basically saying this is the driver, which is to use the MySQL driver, the database URL. We're giving the username and password here. Probably not a good practice, but this is just a simple application. And this is an interesting thing. So here for the parser, which is in between, we are creating multiple partitions. So here we are saying create 4 partitions for the parser just by a property, right? So essentially you'll get 4 partitions of the parser. The reason is this is just to show that typically in applications the parsers do some heavy lifting, because they are actually converting from the string. They're actually parsing the stream. So this is to show that that you can actually create multiple instances. And one more thing is that the Kafka operator that you have from the library, that is also dynamically partitioned. So it looks at how many partitions are there on the Kafka side, and it creates as many number of partitions on the Apex side or DataTorrent side, because that's the default 1-to-1. There's also a many-to-one, where essentially one DataTorrent partition can handle, or one Apex partition can handle multiple Kafka partitions, but by default it's 1-to-1. So you'll see multiple Kafka partitions. They're being automatically created because of dynamic partitioning, and you'll see multiple partitions of the parser, which are statically created because you defined them here. Okay, so now our application is pretty much ready. I'll just have to build it. So I'll go here and I'll just run the standard Maven commands, which all of you are probably familiar with, to build a Maven project. So if it's successful, in the target folder, you will see a file which ends with .apa extension. So this file contains basically it's like an application package. So it contains your code, everything that's compiled. I mean, it's a compiled of all your classes, your jars, any dependencies that you have, any resources that you have, properties, everything in one app package. This is an analog or equivalent to the web world, right? In a web world, when you build your project, you get a WAR file or you deploy a WAR file. So it's kind of like that. I mean, just an analog, right? There's no similarity between the two file formats or anything like that. So now you can now deploy this. If you're using DataTorrent, you can use our UI tool to deploy this. Or if you're using Apex, you can use the command line to launch this. But everything is self-contained in this one app package, right? So now I'm going to go to our console. Okay, I'm going to go to this tab called Develop in this application package, and I'm going to upload the package. So I was in Meetup app and target, and I'm going to take this APA, upload it. So there's a question, I have not defined a unifier, how to scale the counter. Good question. I would definitely cover it if we had more time, but please look at our library operators and you can see how they define the unifier. So right now I'm not going to partition the counter. So we have the Meetup application that we just uploaded, and if you have multiple applications in the package, you'll see them. Here we only have one. You can right click here, you click launch here, and it'll launch it. So now it's actually getting resources from Hadoop. It's basically launching the first container, which is our application master. Then the application master is analyzing and launching, getting more containers for each of the operators, and basically launching the containers for each of the individual operators. And so, yep, all of them have started. So you can see that the DAG we just built with input, parser, counter, and output, right? The one we just built, input, parser, counter, and output is ready. And it's running, all the operators are ready, and you can see for every operator you can see on its last heartbeat the CPU usage. And if you go to the physical view, you can actually see there are multiple so our Kafka topic that we chose has two partitions. So two partitions got created for the input operator, and then we said we want 4 partitions for the parser, so the 4 partitions for the parsers got created. And when you don't specify a unifier, we have a default unifier that we insert, which is essentially just a stream. It just concatenates the two streams. But if you have your own unifier logic where you're doing more different logic, that you can specify that, and that'll get placed there. So in the case here, we're just going to take lines from the input and send it to the parser. So that's okay. We can just merge the two streams, and the counter and the output. So now let me send some data. So this guy is reading from a Kafka topic. So let me send some data to the Kafka topic. So I have a command line thing here, which essentially is sending a reading of. This is just a Kafka command line producer, console producer, which is just a simple program to send the contents of a file to a Kafka topic. So I'm just sending it to Meetup, and the file I'm picking is the Kafka license file itself. So I'm just going to run the script. So essentially, it's going to start sending data to the Kafka topic, and you can see data is arriving in our DAG. So we are reading from Kafka. So we are already starting to process the data, and once it's done, we'll go look at the. So it's done. So now the data should be in the MySQL tables. So if you remember last time, the word count had nothing. So now we have the counts. So let's pick something. Let's say the word contribution is 8 times, right? Now let's run it again. We'll send the same file again. And just to show you that it's cumulative counts, right? It's not like it's losing the old counts. It's basically keeping it. So let it finish, and we'll go back and see if it became 16. There you go, right? And if you remember, we are not doing any additions on the MySQL side here. We're just doing it in the operator is keeping the cumulative count, because the JDBC output is just doing an upsert. It's always doing, and if the value is already there, it's just changing, totally overriding it the first time it's inserting it. So that's it. It's how easy it is to write applications and deploy them and run them and monitor them, and look at them, look at each operator, see where it's running. Each partition you can see where it's running. For example, there are two partitions at the input. One was running on node 22, one was running on node 17. You can look at the memory. Whole lot of thing here, right? If you are an operations person, you can have a very detailed view of every part of your application. You can even record data that's going in and out of the operator. So yeah, so that's about what I wanted to show you today. And hope hope you guys liked it, and hope you're able to hope you'll go and try Apex and DataTorrent and build your own applications. So any other final questions before we can end? There's a question: is there a SQL statement for each end window? Yeah. So in this particular thing, I think there's a transaction that's happening every end window, and it's basically committing the transaction. But the inserts are happening as the data comes in, and it's and there's a batch as well. So it's not like it's sending every insert to the database immediately. Is it possible to share template and the example project? I will share all the I'll share the template, probably put it on GitHub, and of course the slides and the video as well. Okay, so good. Thanks everyone for spending this Saturday morning. I know you probably had other plans, but thank you for taking the time to join the talk, and have a good day. Bye. Going to stop broadcasting.